Hi, I'm Graham Lewis. In this interval we're going to study confidence intervals, which is really useful and will help you not only in this course but also when you read articles in the news media to understand when they talk about confidence intervals and margins of errors. Let's have a look at this article from the CBC. Now here they say with the title, most Canadians who switch careers are happier for it, survey finds. Now obviously they haven't asked everyone in the whole of Canada if they're happier when they switch a career. They've taken a sample. Let's have a look what they say about that and what their estimate is. So you can see here that 87% of people, is their estimate, said they are happy since they made the change. But this is the really interesting thing. And the margin of error is plus or minus 3.1 percentage points 19 times out of 20. What does that plus or minus 3.1 mean? And what does 19 times out of 20 mean? We're going to explain. So let's start with the plus or minus 3.1%, which is called a margin of error. So if we take our estimate of 87% and we add 3.1%, we get an upper bound for our confidence interval of 90.1. And if we subtract 3.1% from 87%, we get our lower bound for our confidence interval of 83.9. So that's what the plus or minus 3.1% means. The 19 times out of 20 is a harder concept. Let's try and explore that. Now, imagine we don't only have one sample. In our first sample, we got an estimate of 87% plus or minus 3.1 percentage points. Imagine we collected 20 different samples. Every one of those samples will have a different estimate. The first one might be 87%, the second one might be 85%, the third one might be 90%, etc. Every sample will have a different confidence interval attached to it, a different lower bound and upper bound. And every confidence interval will either capture the true proportion or not. Let's talk about that. Now, I want you to imagine that the actual true proportion of Canadians, if we actually interviewed every single one of them who changed careers, that 91% of them were happy. Let's imagine that's the true proportion, which we'll never know unless we did a census. In our sample of Canadians that changed their job, in our first sample, we got 87% here. So that's our point estimate, 87%, which is an estimate of the true proportion. Now, we got plus or minus 3.1 percentage points. So that gave us 83.9, which is the lower bound bracket there, and 90.1, which is the upper bound. You can see that our sample, if the true proportion was 91%, did not capture the true proportion. That's a shame. And that's what happens. Sometimes it will capture it and sometimes it won't, and you'll never know. However, with the use of probability, statisticians do know that they can set the probability of how many times the confidence interval captures the true proportion. So imagine sample 2, and maybe that was a 91.5%, and that confidence interval captured the true proportion. You can see that the 91% is inside the interval, whereas here the 91% is outside. Let's imagine sample 3 also captured it, and sample 4 also captured it. And let's imagine all of the other samples up to 20 all captured the true proportion, apart from our first sample which we got, which didn't. So sample 1 happened to be the only sample that did not capture. So that's where the 19 out of 20 comes along, which is of course equal to 95%. So this is a 95% confidence interval, because if we were to collect 20 samples, different samples, 19 of them would actually capture the true proportion. And that's what our confidence interval is. What we can't say is that there's a 95% chance that the true proportion lies in the interval. The true proportion either lies in the interval or it doesn't. What we can say is that if we collect 100 samples, we would expect 95 of them to capture the true proportion, and that's what a 95% confidence interval means. So this is a summary of that. For a 95% confidence interval, if we had 20 samples, we would expect 19 out of 20 of them to capture the true proportion, or 95%, which is good, and that's the most common one we often use, 95%. A 90% confidence interval, we'd only capture it 90 out of 100 times, or 18 out of 20. And 99%, which is very confident, if we had 100 samples, we'd expect 99 of them to capture the true proportion, which sounds really good, but I have more confidence. So I wonder why statisticians don't always use a 99% confidence interval if it gives more confidence. And we'll show that in another video when we look at the mechanics. However, in reality, we don't collect 20 samples or 100 samples. We only collect one sample. And so we never know if our confidence interval has captured the true proportion or mean. It either has or it hasn't. But if we take the biggest sample we can, which is always a good thing, we can actually narrow the width of the confidence interval and have high confidence. So what we can control is the size of our sample. So the bigger the sample, the better, because we can be more confident and have a narrower width. So that's a really key idea. This is how to interpret your confidence interval, and it's this sentence here, and you just fill in the gaps. So I am % confident that the true of is between and okay? And all you have to do is fill in those gaps. So in our example we just did, I am 95% confident that the true proportion of people being happier after making a career change is between 83.9% and 90.1%. So that's a lovely way to interpret your confidence interval and how to write it down when you're writing your statistical reports and giving your confidence intervals. Now, when we look at confidence intervals, we actually need to find out the critical Z-star values. And this is working backwards. So basically, here's my 90% confidence interval where the area is 90% in this shaded region here, which means we've got 5% at the upper end and 5% at the lower end, not shaded. So to find out this Z-star value, which is critical, and it's called a critical value, to find that we need our Z-score tables. Now, unfortunately, our Z-score tables only work from the left, going all the way up to a point. So if you think about it, if we look at this picture here, going all the way from the left here, all the way up to our Z-score, we're not including that 5%. So I need to find an area of 0.95, 95%. And so we're going to look at that on our Z-score table. So here's our Z-score table, and you can see I've actually highlighted the three 90% one, the 95% one, and the 99% one. But let's just talk about the 90% one first, because we were looking at that. So I'm looking for an area of 0.9500. And there's actually two. There's 0.9495 and 0.9505. And statisticians always take the 0.9495, and so it's a Z-score of 1.64. So that's how we did it. In the 95% one, you'll see that it's 1.96. And for the 99% one, 2.58. And I'll show those quickly as well. So for the 95% level, which is the most commonly used, and you'll see it in a lot of news media, 19 times out of 20 when you read a margin of errors in elections and all sorts of things in the newspaper, lots of medical reports, etc. So if we want 95%, that means we've got 2.5% at both ends. So thinking about the cumulative, I want to find the Z-score that matches in my Z-score table for an area of 0.9750, 97.5%, which comes out as 1.96. So that's how we do that. And similarly for the 99% one. So for the 99% one, if you think about it, we've got 0.5% at the upper end and 0.5% at the lower end. So that gives us the full 100%. So in our Z-score table, we're not including this 0.5% going from the left all the way up to the point. So we look for 0.9950, 99.5%. And that gives us 2.58. Now, the nice thing is you can kind of memorize this, and here are the confidence intervals and the corresponding critical values which we'll need to work out confidence intervals, and they're always the same. If you choose a 90%, it's 1.64. If you choose 95%, it's always 1.96. And if you choose 99% confidence, it's always 2.58. So that's it. In my next video, we'll actually do a confidence interval for proportions and go through a worked example. Have a great day, everyone.